This lesson is on 13.6, the normal curve, and we begin looking at a histogram. In this particular histogram, you see that this middle class has the highest frequency, and then it kind of tapers off to each side, but it has what we call a normal distribution. And if we were to look at that histogram that's symmetric in nature, and actually the center here would contain the mean of that data. If we look at it here in a couple of different, we call these bell-shaped curves. So it's just the histogram, but we've kind of curved that look just a little bit. We're still going to represent all of the data on these different graphs, but we look at these three are all bell-shaped curves. They just all have a different shape. So each one of them is symmetric, and each one of them, the middle here would be the mean. So same thing here and here would be the mean of the data. And then you can see here some properties of a normal distribution. We say that the graph is called a normal curve. It's bell-shaped and it is symmetric. So if I folded that on the line that I've drawn, you can see that it produces a mirror image. And the mean, the median, and the mode all have the same value. So not only is this the mean, but it's the mean, the median, and the mode. They all occur here at the center of the distribution. So let's look a little bit more in more detail at that normal curve. Here we've got the normal curve and what we call the empirical rule that says that under that curve, and remember that the middle here would be the mean, approximately 68% of all the data lies within one standard deviation of the mean in both directions. So if here we have the mean, we actually here have the mean minus one standard deviation, and then in the other direction this would represent the mean plus one standard deviation above the mean. And then 95% of the data is going to fall between, or it lies between, two standard deviations of the mean in both directions. So here that would be the mean minus two standard deviations, and here this is the mean plus two standard deviations. Let me get that right. Okay. And then also 99.7, so that's almost every bit of your data, lies within three standard deviations of the mean in both directions. So this would be the mean minus three standard deviations, and this would represent the mean plus three standard deviations. So let's say, and I'm going to use the example they've given you in the book, let's say that there is a mean of 100. So if the mean of the data is 100, and we know that there's a standard deviation of 10, then one standard deviation above the mean, that would be the mean of 100, plus 10 would be 110, whereas the mean minus one standard deviation would be 90. So we would see that 68% of your data would fall between 90 and 110. And then we also could look at, let's keep going further. In fact, let's go ahead and fill this out. So plus two standard deviations, I would have 100 plus 20, and then 100 plus 30. So 120, 130, and in this direction 100 minus 2 times 10. So that would be 100 minus 20 is 80, and this would be 70. So we would say that from our chart, 95% of the data would fall between 80 and 120, and then 99.7% of my data would fall between 70 and 130. And there may be some outlying factors there But if we're told that data has a normal distribution, then those percentages would be true for no matter what data you were dealing with. Now we look at z-scores, and we're going to use z-scores, or they're also called standard scores, to determine how far in terms of standard deviations the given data value is from the mean. So each piece of data, we're going to standardize that piece of data and make it a z-scored or a standard score. And a z-score of, this says for example, a z-score of 1.5 would mean that that piece of data is 1.5 standard deviations above the mean. If it's negative, it would mean that it fell below the mean. Now let's look at how to find a z-score. The formula for finding a z-score would be using the value of a piece of data minus the mean and divide that by the standard deviation. Standard deviation could either be given to you in the problem, or you know how to find it from the work that we did in section 13.5. But in symbols, I'm going to represent the piece of data with an x minus x bar over s for standard deviation, and we did use standard deviation of, most of these are in just a sample set. However, another way of writing this formula, if you were using data from a population, would be the piece of data minus the mean, which would be represented with mu, over standard deviation, written that way if you were looking at a population. I'm going to stick with this one. Let's look at an example. This example says the mean height of men is 69 inches with a standard deviation of 2.5. Find the z-score for a height of a man 74 inches tall. So when we find the z-score, the standard score, one way of noting that would be we're going to use that that piece of data 74, just so we'll remember that that's what we're finding the z-score for. And then the formula would be the value of the piece of data, so 74, minus, we were given that the mean was 69 inches, divided by the standard deviation given in the problem of 2.5. That would be 5 divided by 2.5, which gives me 2. So I get a z-score of 2, and what that means is that this piece of data falls 2 standard deviations above the mean. So from our normal curve that we saw before, we saw that the mean was 69, so 2 standard deviations above the mean would be this 74. Okay, I guess I could draw that a little bit better. And then let's do a couple more. Let's look at, what if the piece of data, what if I had a man who was 66.5 inches tall? Then the z-score would come from the piece of data, 66.5, minus the mean, 69 was given in the problem, divided by the standard deviation of 2.5, which would give me a negative 2.5 divided by 2.5, which is negative 1. So this piece of data would have a z-score of negative 1, meaning that the piece of data on the normal curve would fall 1 standard deviation below the mean. So this piece would be 66.5, 1 standard deviation below the mean. And then let's do one more. What if I wanted to know the z-score of a man who is 69 inches tall? So the piece of data is 69 minus the mean, which we already said was 69, divided by the standard deviation of 2.5 gives me 0 over 2.5 is simply 0. And then that would be true that the piece of data, if it's the same as the mean, would have a z-score of 0 because it does not fall any above or below the mean since it is the mean.